Okay, so we can slowly start again. This lecture now is going to be about basic modeling with binary variables. We'll see some of the things we saw in the previous lecture again, just to reinforce it. And then the next lecture will be about more advanced modeling with binary variables, including support vector machines. So I'll talk about some modeling practices and then give you the main points again of this lecture. So this book, this reference to Williams was up before. Modeling is really important for mixed integer linear optimization. And it's even more important in mixed integer nonlinear optimization. We saw in the last lecture that we can make easy mistakes by formulating integrality conditions, for example, as nonlinear equations. And because we have this flexibility now of modeling both integer and nonlinear functions, it's good to pay a little bit more attention to how we do the modeling. In particular, it's good to always reformulate things, relationships, so that they're convex. And the interaction of nonlinear functions with binary variables can also be sometimes tricky, and we want to avoid modeling mistakes there. And then this is a sort of general statement that we always prefer linear over convex over non-convex formulations. And the great divide between being able to solve problems at scale efficiently and not is this difference between convex and non-convex. So once we're convex, we have a fairly good handle on solving large problems. Non-convex is much harder. Okay, so here's a theorem from Jeff Lindroth, who is a great mixed integer nonlinear optimizer. He solved more mixed integer nonlinear programming problems than anybody else in the world, and he says that 97.238% of all MINLOs have integer variables for two purposes only, namely to make multiple choices or to use them as indicators to turn on and off continuous variables or constraints. And so you should take this with a grain of salt. Of course, we haven't looked at every single mixed integer nonlinear optimization problem. Multiple choice selections appear often. For example, you could have pipe diameters that you're selecting. If you're designing a water network, the diameter of the pipe basically tells you how much water you can pump around. But pipes are more expensive if you have larger diameters, and it's also more expensive to operate. So you want to fit the diameter pipes to your network. And they don't come as continuous variables because they would have to be manufactured especially for you. So instead, there are discrete choices. And the second one, as we saw in the last lecture, where we had a binary variable that if it's switched on, then we want to enforce a constraint. And this could be a constraint that has something to do with a particular unit that is being switched on. And if the unit is not switched on, then there are no constraints on the variables inside that unit. So if you're not switching the unit on, you're, for example, not using any electricity or other things. And this should be not enforced. Apparently, I'm not very good at putting text in text. So how do we model discrete choices? That's actually very, very easy. And I think many of you have seen that. There is this notion of a special ordered set. And in this case, you have a number of binary variables, and you have one binary variable per discrete choice. So there were k discrete choices, d1 through dk, and I have one binary variable per discrete choice. And the second constraint here says that exactly one of these binary variables has to be equal to 1. So that means I pick exactly one diameter, for example, out of the choice of diameters. And the diameter that I pick is the one that has a 1 here. So that's the diameter that I pick. That's also called a one-hot encoding if you're a computer scientist. That is a one-hot encoding, so that's another word for it. We'll see in a moment that you can also use this to linearize univariate functions, and it generalizes to higher dimensions. So I'll show that in subsequent slides. So you can do this not just in one-dimensional problems, but higher dimensional problems. And the nice thing is that solvers have a way of detecting this structure. So this is a very special structure. You have a set of binary variables. Exactly one of them is equal to 1, and they appear in one other constraint. And this is structure that you can detect And you can, there's special branching rules that we'll tell you about later that allow us to solve these problems efficiently. So there's an efficient way of solving these problems. And it's actually almost equivalent to writing a specific solver that would branch on discrete values. So discrete values are hard to handle. You can handle the relaxation by just allowing d to be in the interval between d1 and dk, but then it's not clear how you would branch on that. And you would have a different branching routine for different sets of discrete values. And so that makes it very hard. So this is a much better way of introducing modeling it. Okay, so here's a lead up to a little exercise, and Ashutosh Mahajan will talk tomorrow, I believe, about water networks. So you can do this exercise in a moment, and then you'll have a head start on tomorrow's lecture. So we're modeling the diameters of these pipes. That's just copied from the previous slide. Little d is the parameter, is the variable that denotes the diameter of the pipes, and yi are the special ordered set. Now, within this water network design problem, there's something called the pressure drop along an arc. So an arc goes from a node I to a node j. So you now have a network of pipes that somehow distributes water. And one of the modeling equations that is used here is the head HI is the pressure at node I. There's a diameter of this pipe, little dij, and the distance, and I apologize for this double notation, the distance between the nodes I and j is this capital Dij. So I apologize for making, that's not a very nice notation, using capital Dij as the distance. And this equation is one that's been derived empirically. It approximates the solution to a partial differential equation in steady state. Note that there are these funny coefficients, 4.33, that have to do with what kind of medium is flowing through the pipes. So for gas networks, that will be a different exponent. There's an absolute value there, but it turns out that the numerator is actually differentiable, continuously differentiable, because the exponent is large enough. Okay, so HI are the head, QIJ is the flow from arc I to arc J, and Dij is the diameter of arc Ij. Right, so the little exercise here that you can do in the next 4 or 5 minutes, I think, is look at this expression here, 1 over Dij squared. So that's a nonlinear function. And the question is, can you linearize this using special ordered sets? So you have f. We don't need to carry around the subscripts. F is 1 over d. And d is given as this discrete choice variable 1 over d squared. And the question is, can you make this expression into a linear expression? So here's a nonlinear relationship, and I bet you $5 that you can make this into a linear relationship in the next 4 minutes or so. And Pietro will pay you the $5 if I lose the bet. So. Okay, has anybody got it yet? Okay, 1, 2, okay, 3, 4. Okay. Okay, those who haven't got it yet, next time sit next to the guys who get it and copy their work. Okay, so how do I do this? Do you want to tell us?
Simply, instead of having b equals yi, instead of having b equals the binary yi di, we can say that 1 by d squared. 1 by d squared as 1 by d is So 1 by c squared is another variable, and then say that yi by d.
Okay, okay. I think what you're saying is that f of d is, you just gave me the answer, yi times 1 over di squared. Okay, so I'm not as fast as that, so I'm slower. So I start off with, that's what I want to do. I have my nonlinear expression there. This is my nonlinear function. So then what I do is I compute 1 over di squared. I can just pre-compute those values. That's a constant. And then I do this one trick where I just dij squared, I just substitute dij. So that's the expression that I have up there at the very top for the special ordered set. This is dij, I substituted it, I square it. And now I realize, I look at this a long time, and I realize that the only values that this is going to take is 1 divided by dl squared for the particular L that I choose. So I can sort of take out this summation over there. I don't know. This is how I see it, but you have a better way of seeing it immediately. So, and this holds in general, and that always holds because YL is this one-hot encoding. So you can always rewrite these nonlinear functions using this trick, and it's an equivalent reformulation. So that's kind of cool. We've actually used this for an optimal control problem where we were solving an optimal control problem for a quantum system. And that problem is highly non-convex, but when you realize that you have this one-hot encoding, you can actually write down relaxations that are much nicer to solve. And so sometimes this is good. So in tomorrow afternoon's lecture, when Professor Mahajan is telling you about water networks, one of you should say, oh, but why don't you do this one-hot encoding formulation there? He'll be impressed. Okay, so this is just a reminder. We saw this in the last slide, that when we have a constraint that we want to hold when the binary variable is equal to 1, then we model that with this known upper bound. So we find an upper bound on GI of x. It doesn't have to be positive. Oh, sorry, yes, it has to be positive in this case. Here's a cool question, actually, just occurred to me. What happens if the upper bound on g of x were negative? Anybody know the quick answer to that? So, sorry? The constraint is redundant, right? If I can show that the upper bound on g of x is negative 2, then this constraint always holds. I don't need to worry about it. Okay, so m greater than 0 is an upper bound. Then I enforce this constraint with this simple trick here. And I also told you we do not want to multiply binary variable with a nonlinear expression. It violates constraint qualifications, for example, and is also non-convex. Now there's an inverse or a reverse of this indicator, which is called a lookout variable. So this is a variable, a binary variable that's set to 1 if a constraint becomes active. So that's sort of the opposite. You want to take some action if some unit goes above a certain threshold, for example. So what you want to do in this case is you have, for example, a linear constraint, an affine constraint there, and if that is less than or equal to 0, then you want to force yi to be equal to 1. And you can model this by now having little m is now a lower bound on your linear expression or nonlinear expression, and epsilon is a small tolerance, and you probably want something around 10 to the minus 6. The reason is that if the tolerance of your nonlinear solver is 10 to the minus 4, if your tolerance of your nonlinear solver is about 10 to the minus 6, you want the tolerance of the nonlinear solver to be distinguished from this small constant here. But this is, again, this is a modeling decision. So what does this constraint do? Let's just see what happens, again, by plugging in values for yi. So if I do that, then if yi is equal to 0, what do I get if yi is equal to 0? I get AI transpose X plus BI is greater or equal to 0. Right? And if well, that's not the right way around though. Sorry, I wanted the other way around. So I'm going to look at my constraint AI transpose X plus BI. And if it is positive, then the only way I can make it positive is if I set yi equal to 0, then that's not correct. So I need to make yi equals, if it's positive, I need to make yi equals 0. Yeah. Sorry? Did I get this?
Make it positive, either would work. Even one would work. Because your M is a lower bound.
Right. There's something not right here. I need to check this.
No, we don't care if it's positive. We only want.
You only want it if it's less than or equal to 0. If it's less than or equal to 0, then
so you want yi to be greater or equal than some than a quantity, means a quantity is greater than 0 when the ax plus b is positive.
yeah, there's something not right here. I need to check this. Okay, we'll come back to this. Here's another little problem that is quite old now. It's sort of optimizing an old kind of broadband networks on resource sharing meshes. And the objective there is to minimize interference between channels. And to do that, you can assign channels to basic nodes within a network and look at when channels in the network overlap. And so there's this sort of this channel interference if you have two access points with the same channel. And so this is in general a non-convex mixed integer nonlinear optimization problem. And the model that I found in the literature has this really horrible constraint. And this is the constraint here. So it's the constraint is z is equal to 1 divided by 1 plus 1,000 x minus y to the power 10. So I've plotted the constraint on the right-hand side here. And so this is plotting z versus the difference between x and y. So on the x-axis here, you have the difference between x and y. If x and y, if the difference is large, then, sorry, let's go with the difference 0. If the difference is 0, if x is equal to y, the difference is 0, then you have 1 divided by 1 is 1. If the difference between x and y is 1, then you have 1 to the power 10, which is 1. So you have 1 divided by 1,001. And if the difference is 2, then you have 2 to the power 10 times 1,000 and invert that. And so this constraint is really horrible because it's got a lot of curvature. It's a very, very nonlinear constraint. It would be horrible to solve this problem. But there's a cool model. You can model this using binary variables. Really what the constraint is saying, and you need to look at this nonlinear constraint a little bit and plot it. What this constraint is saying that z is equal to 1 if x is equal to y, and z is equal to 0 if x is not equal to y. That's what they're trying to say. Now, it's not exact. Notice that this constraint here is different because this function is actually never 0 because it's 1 divided by a massive number. Okay, so in the next This is a bit harder, so we'll do this in 10 minutes or so, I think. But see if you can model this using binary variables. So I should tell you one more thing, that x and y are integers in this model. So I forgot to write this on the slide. So we have x and y are integers, and we can assume without loss of generality that x and y are in a finite set. So let's say 0, 1, just make it even easier, 1, 2, up to capital K. That's all you need to know. And then you want to model the condition that z is equal to 1 if x is equal to y and 0 otherwise. So you want to model this condition using whatever you have at your disposal. So, and while you're doing that, I'll try to figure out the other question. Has anybody got it? One? Anybody? You got it? Half. Okay, half is good. You've got it? Okay, what do we do? Okay.
Then x minus y should be less than equal to k into 1 minus z.
X minus y will be less than or equal to k times. Okay, let me see this. So you've got x minus y less than or equal to k. 1 minus, okay, 1 minus z, yep. Minus k. Okay, so does that do it? If, let's see, if x minus y is 0, so we're going to check x minus y is equal to 0, then I get 0 is less than or equal to k times 1 minus z, and 0 is greater or equal to minus k times 1 minus z. But that doesn't, I don't think that tells us that z should be 1. Because I, no, because, so let's say k is equal to 10, right? Then, so make this 10. Then this would be 10 and minus 10. And so all I'm saying is that 0 is between, sorry. Now all I'm saying is 0 is between, so z could be 0. And then this just says 0 is between minus 10 and 10. So z equals 0 is feasible here. And z equals 1 is also feasible.
It takes care of one case. Though.
What?
So it takes care of one case. So if z is equal to 1, so
yeah, if z is equal to 1, it does the opposite. It does exactly the opposite. You're right. If z is equal to 1, then x is equal to y. So we've done that case.
X minus y is equal to 1 minus z. That half is completely right. X minus
Okay,
y.
we have another one. Wait. Okay, let's do the next one. So you're saying x minus 1 is equal to?
X minus z, x minus y is equal to 1 minus z. Almost similar. So whenever the x is equal to y, definitely z will be 0.
X is equal to y. then z is equal to 1. Yeah.
Z equal to 0.
Okay. So the first case is x is equal to y implies z is equal to 1. But what if x is 10 and y is 5? Then I have 10 minus 5 is 1 minus z.
So it is 5. So Z will, it is minus 4. Z is equal to minus 4.
Right.
So we have to put a condition that Z can only take greater than 0 values or
Okay, but that makes this infeasible now if I put that condition there.
half one.
Okay. You have another one.
Z should be less than equal to x minus y plus 1.
Okay, let's try that. Z less than or equal to x minus y plus 1.
And z should be greater than equal to minus of x minus y plus 1.
Minus x plus y. Minus 1 or plus 1? Plus 1. Okay, this looks good. Let's check it. So if x is equal to y, z is less than or equal to 1, and z is greater or equal to 1. So z is equal to 1. Good. Okay, I like this. And if x is not equal to y, then we get
So that depends if x is greater than y or y is greater than x.
yeah, but I don't think I get it. Because let's try again. Let's try the same again, right? If x is 5 and y is equal to 10, then I get z less than or equal to 5 minus 10 plus 1 is minus 4, and z is greater or equal to minus 5 plus 10 plus 1, so minus 5. 6. Oh, unless I made a mistake. Okay, I have another solution. Can I show you my? Who did it with special ordered sets? Let me ask that question. Did anybody use special ordered sets? No, I need, Pietro, I think I need your password again. Sorry about that. Okay, so here's what I would do. I would write x as vi times I equals 1 to k, and y as I equals 1 to k wi times I. So I have two special ordered sets. Okay, and then I realized that x is equal to y. So I now have I have these two encodings of my integer, and x equals to y. What does that mean? That means that I have the same binary string for both, right? So that means that the vector v has to be equal to w, okay? Because they both pick out the same integer. So v and w are vectors of zeros and ones, so 0, 0, 1, 0, 0, 0. If that's v, 0, 0, 1, 0, 0, 0, that's my encoding of, so this is x is equal to 3, y is equal to 3. So and they're both the same. And a way of saying that they're both the same is to say v transpose w is equal to 1. Right? If v and w are the same vector, then if I multiply them out, I get a 1. And if they're not the same, then I get a 0. So this is, so if x is equal to y, or if and only if, and v transpose w is equal to 0, if and only if x is not equal to y. If they're not the same, then that's the case. So I'm going to say z is v transpose w. And I see some of you looking really suspicious at me now because I'm just multiplying binary variables away. I'm introducing nonlinear expressions. This can't possibly work. But this is what we do. So we introduce these binary expansions of x and y. So we lift the problem, we introduce additional variables. We make the problem harder in many ways. And then we observe that x is equal to y if the v components and the w components match exactly. That's the only way they can be the same. So I have to have the same one-hot encoding here. And that's equivalent to saying v transpose w is z. So that if I multiply two binary vectors that have at most one non-zero together, they're either 1 or 0. And they're 1 if they're the same and 0 if they're different. Because then if they're not the same, then these numbers don't overlap, right? If I have a 0 and a 4, or 3 and a 4, then if I multiply them out, they're 0. Okay, now I just need to get rid of this nonlinearity here, but that's a trick that we learned earlier. So I now introduce a binary variable Si, which is Vi times Wi. So V transpose W is the sum over all I of Vi times Wi. So I introduce this binary variable, and now I use the trick from earlier, and I missed something on my slide. So I can rewrite this condition equivalently as Si less than or equal to Vi, Si less than or equal to Wi. So if either Vi or W are 0, then this will make Si 0. What I forgot here is a plus, a minus 1. There should be a minus 1 there. Okay, so I need to put that on the slides. This is a minus 1 there. So if both Vi and Wi are 1, then these two just say Si has to be less than or equal to 1, and this says Si is greater or equal to Vi plus W minus 1, so 1 plus 1 minus 1 is 1. So I introduce a variable Si that's between 0 and 1, and in fact it's an implied binary variable, so I never need to branch on it or do anything with it. Si, whenever Vi and Wi are both binary, Si will also be binary. And I forgot the same condition here, so that should be Vi plus Wi minus 1. And in fact, there's a theorem that says so this expression here is the convex hull. I'm going to write it out on the board because I want to make sure we don't copy anything down that's not correct. We don't want mistakes on the slides. So the condition is that I want Si equals Vi times Wi, and that's equivalent with, for these binary variables, which is saying Si is less than or equal to Vi, Si is less than or equal to Wi, and Si is greater than or equal to Vi plus Wi minus 1. And you can just easily see, if you plug in binary variables Vi and Wi, if both of them are 0, then Si will be 0. If one of them is 0, Si must be 0. And if only if both of them are 1, then you have less than or equal to 1s here and greater or equal to 1 down here. And that's it. I don't know if there's a better formulation. So if you have a better formulation than this, let me know. But when you guys came up and said, oh, we can do this without the binary expansion, I thought there was a better way of writing it. Maybe there is. I don't know it. But this is one way of doing it. So you do this calculus with binary variables. That's what you're doing. And it's okay to be a little bit nonlinear because multiplying binary variables gives us these implied binary variables. So there's a theorem that says if Vi and Wi are binary, then Si is also binary. And that's why it's called an implied binary variable. Cool. That's it. That's the model. So that's actually a really nice model. So yes, sorry, Pietro.
So this uses one fucking coding, and I guess it's really good when K is not too large. If K is very large, does it make sense to use a binary expansion where instead of the I multiplying the V and the W variables, you have actually power to
Right. So Pietro asked if k is very large, should we use a binary expansion? So instead of vi times I, we use vi times 2 to the I, and we go maybe from 0 to k. And we can use the same here.
No.
So what's so somebody has the answer. So can somebody answer Pietro's question? Where does this break down? Sorry? We can't do.
No, wait. The second constraint shouldn't be there.
Oh, yeah, the second constraint is not there. Okay, I'm going to have to remove that, yes. Otherwise, we only get, so we remove this constraint. Okay, and this is still true, so V is equal to W. So everything up to here is okay. But I don't know how to use this trick now. So V transpose W is no longer 1 because this is now a binary encoding, and so the binary encoding of. Can somebody tell me which number this is? This is 1 plus 2. This is 3, right? That's the binary encoding of 3. But now it's not 1. So this no longer holds. So that breaks down.
Yes,
I think.
You need to use the exclusive OR or something.
Yes, I don't know how to do that. So Pietro will tell us in his lecture how to do this. But that's a good point. This is fewer variables because I just need to look at the log 2. I can go to larger k, right? The log 2 or exponential of k. Cool. Okay, so more exercise. We don't need to do this. Now, SOS1 variables, they're really cool. This one-hot encoding, I just love it. And there's a bit of calculus that goes with it, and you just need to figure out the cases. We talked about indicator and lookout variables, and please never multiply a nonlinear function by a binary function. Except when you want to do cool stuff with binary vectors, then you can do other things. You're allowed to do it again. But that's it. So you have a question, yes? Right, so, okay, so I will not use this expression. This expression, the 1 over 1 plus 1,000 x minus y to the power 10, I delete that. Correct, yes. So what I add instead is the constraints down here with the minus 1 after vi plus wi. Okay, so you think this is not good? You don't like it? It's good. It's a lot more variables, right? Instead of having 3 variables, x, y, and z, I still have x, y, and z, and in addition I have 1, 2, 3k additional variables. But this is linear. This is a linear expression. If you look at the Hessian of this term, it's horrible. You can write down the Hessian, but it will have massive term. There's a lot of curvature here. I mean, this just goes up to 1 very fast. So it's
Was it a nonlinear attempt to write the expression below? So is that nonlinear expression used just because it approximates the expression below?
I think so. The authors don't say that. So I read the paper, and this expression just pops up. And they just say, here's this is what we use. And you need to plot what's going on, and then you realize why this is there. So I don't give you the reference. I don't want to talk negative about authors, but I think this is a nicer formulation.